All right, so it's a great pleasure to introduce Cadet Mackenzie Harrmann, who's been working with me this year. She's been working quite hard, and she's going to tell you about vibrating cantilever. As exciting as that sounds, it's actually very interesting. Lots of good physics and lots of good math in it. Mackenzie?
Thank you. My project was involving a vibrating beam and looking at different ways to model it versus, measuring it and seeing what ways which model worked best. Okay, so there are quite a few different ways to model vibrating beams. It's been, beams play a really important role in engineering, especially when they're vibrating, because nobody really wants your whole structure to come down. So there's been a lot of studies that have gone into beam theory and especially vibrating beams. So here, this is what we mean when we say a cantilever beam. So that just means that one side is fixed and the other side is free. So that's the kind of beam we're working with here. There's a lot of others, fixed point, there's both sides anchored, but this one in particular is one free end and one fixed. And so the models I'm going to look at specifically are the Euler-Bernoulli beam theory and the wave equation here. And then this is just another example of a fairly common one. So for the first of the models and the simplest of the models is the wave equation. And it wasn't originally derived to use as a vibrating beam. It was derived to represent a wave on a stretched string. So the idea with using it for a vibrating beam is that the beam actually vibrates as if it was a string or close enough to it that we can approximate it using this equation. And the nice part about this is we're only using second order partial derivatives instead of fourth order, which is what the rest of the beam equations are. So we've got our second order partial in respect to time and within respect to space. If we were doing more dimensions, this could be expanded, but because we're in a single dimension on this beam, we're only looking in the x direction. So, and then we have our tension divided by the mass density of the string. And this is only in the case of a string. We have to adjust this a little bit. We'll see in the next slide to work with a beam. So here we've got our wave equation again, but here's what we're looking at when we're looking at the beam. And this is Young's modulus, and it's a just kind of defining term based on the material of the beam. So this is taking our place of tension in this case. Oh, wrong way. There we go. Okay. So because this is a second order partial differential, we need two boundary conditions and two initial conditions. So for the wave equation, it's pretty simple. We need a boundary condition at each end of the beam, and those are taken up here. So we've got a fixed end, and then we've got a free end. Then we need initial conditions for the initial placement in the x direction. So we've got what position the beam is in, so like if it's starting at 0 in this case, what position it's in when we start, and then what the velocity of it is when we're starting. There we go. Okay, so then the other model we're looking at is the Euler-Bernoulli vibrating beam equation. And this is a slightly more complicated one because we're looking at a fourth order partial. So this is even actually a slightly simplified version of the model. It can be expanded out to include a lot more parameters on the beam, but here we're looking at, here's the Young's modulus again, the second moment of area of the beam's cross-section. And then we've got our mass per unit length again. So in a normal situation, in a non-uniform beam, these can be dependent on x, which makes this a much more complicated project or model, but we are not dealing with that. We are dealing with a uniform beam, so E and I are independent of x, as well as the mass density. Our equation simplifies down to this. It looks very similar to the wave equation, except we've got a fourth order right here, which complicates things and increases the amount of computation power we need for this. So for this, because we have a fourth order partial differential equation, we need 4 boundary conditions for the edges. So we need an initial position on that bound end, and we also need an initial velocity on that bound end. That's going to be 0 because it is, secured. And then on the far side, we're looking at a couple slightly more obscure conditions. We have a second order and third order partial on the other side. Yes, so here, far end, and this is L, is at the end of the beam where it's vibrating, or it's loose. This is the bending moment. So when we talk about the bending moment, it's how much one infinitesimally small piece of the beam bends in comparison to the point before it. So by saying this at the end, we're saying that it's at the end, so another piece coming after it is not bending on it, basically. And then we have the shear force here, which is 0. And the shear force is just if you're taking a beam, it's this movement. It's like displacement between the two elements of the beam. And because once again, we don't have any continuation of the beam after that, that is also 0. So our initial conditions are going to be the same for the wave equation because we have the same second order partial in this case. So in order to model these, I used the explicit finite difference method. There is an implicit method as well as a couple other ways of doing it that can be more computational power. So I chose the simplest one to keep it to a very bare minimum comparison. So here we've got our second order partial in respect to time, our second order partial with respect to space, and this is just the central difference theorem for a second order partial. And then here, of course, we've got the central difference theorem for a fourth order. And we'll see on the next slide how this can be calculated. But you can see here already we're getting into the I+2, I -2 range, which is why we need the extra boundary conditions. So here's for the wave equation. We've got our central difference for second order here, and this is kind of what it looks like. So we're looking at a matrix that represents, we've got time going up in this direction and the length of the beam going this way. So each of these rows is the place of the beam at that time. So this would be time 0. Well, actually, it wouldn't be time 0. This here is time 0. This is time -1, which is the reason we need that initial velocity. We can get into using a backwards difference theorem to find out the time back a step in time, or find the placement back a step in time. So we use these 4 values. We've got, this is one of our initial conditions here. These two are initial conditions here, these 2 lines. So we use these 4 pieces to calculate this next step here in time. So we're calculating along the x direction and then up through time. So we calculate first in the x, find out the entire row, and then move to the next step in time. Okay, sorry. There we go. So now we get to, so we've got, for our Euler-Bernoulli, we have our fourth order. And this gets a little more complicated because if you see here, we're going forward and backwards 2 steps in time in the x direction. So we've got here, we've got these 6 are what we're using to calculate our next time step. However, if you notice here, we need these columns to already be determined, as well as both of these columns. So these were our initial conditions. So we got our initial position, and then using our velocity, initial velocity, we can calculate this position here. Over here is where we look into our sets of 4 boundary conditions. So here we've got our initial position is going to be 0 because it's secured. That's what I'm looking for. Secured on this end, and then we've got, using that, we can calculate out another time step with a forward difference approximation here to determine what it would be one movement in from that secured position. Then we also have an issue with it on this other end. We're going to hit a point where we need both of these to be determined. And that's where we come into that second and third partial derivatives of our function. And those you can use it ends up being kind of an implicit way. You use you currently have here to calculate forward one time step and then forward another time step, so that you can use that to find your next, position, forward one position and forward a further position, so that you can calculate your next time step. Okay, so then that brings us to the actual experimental part of this. And we originally set it up to be using laser Doppler vibrometry, but we realized that the wavelengths, the amplitude of the vibrations weren't high enough for it to be that, so we used it's a simple Michelson interferometer, which if you've had optics, you should know about. So here we've got our light source, and this is connected over here to a laser. This is coming in on a beam splitter, which splits the light between this mirror and the beam, which is back here. You can kind of see it. So it splits here. The light hits the beam and comes straight back through into our photodetector. And then this light bounces off our vibrating beam, comes back, and also goes into that photodetector. So we're measuring the difference in path lengths between these two paths that the light has to take. So as this is moving, the difference in path lengths between these two is going to change as well. Okay, and you can see here, it's barely visible, but there are tick marks right along here, and those are placed every centimeter. We took a measurement approximately every centimeter of the beam to measure. We were looking for what the nodes and antinodes were of the beam when it was vibrating. So at each of these points, we aimed the laser and then measured the difference in the two signals coming in, how big the difference was in the two signals. One that had a bigger difference was going to be a point where it was vibrating, and then one that had a very small difference was going to be one of those still points in a standing wave. So this is not a great picture because it shows a little bit of outside noise coming in from the beam. So what happened here was I actually walked past the beam right before taking this picture and set it to vibrating a little bit more than it was supposed to be. So that's why this larger wave is coming through here. And the solution to that would be just let it settle again before I take the measurement and then not walk so close to the beam next time. But you can see, what I want to illustrate here is how the measurement was taken between the path differences. So we've got here, this is one peak-to-peak voltage, and this size of this was what determined how big our path difference was. So if this was really big, we were getting a lot of movement in the beam, and if this was really small, we were getting almost no movement in the beam. And you can see here, this is where we determined the change in voltage. So this would, for a normal situation, it would just be a fairly steady even wave throughout. And there wasn't a whole lot of noise. There were a couple of spots that there were, but this would just be a straight across wave function, and we look at the change in voltage there. There we go. So this is not showing up very well, but so here's all of our measurements for the change in voltage between these peaks. So here's the first measurement was most likely at an area of movement, which at a node. So here we've got this one, and those ones are clearly areas where there's a lot of vibration going on. And then we look down here, we've got this one was less than 1 millivolt difference here. So this was clearly where there wasn't or hardly any vibration. We were very close to that point with no vibration down here. And then everything in the middle is kind of where we hit kind of on the way up or on the way down. So we've got some areas here, and if I were to do this again, I'd probably take more frequent measurements so that we have a few more of these high and low values right here to compare against. But this is what I have to work with at the moment. So you can see here, those are the ones we're going to focus on because they're the easiest to pick out. There we go. So this is our the wave equation approximation, and the amplitude is not what it actually is on the beam. I used the generic amplitude because we weren't necessarily needing the amplitude, and it was easier to see than if we had an amplitude of less than a tenth of a millimeter movement. So this is just an amplitude of 1 to simplify things. So if we look here, what we want to do to match up our accuracy of the model with the data is to find these peak points and find these low points. So this peak is at 23.8, I believe it was. So what we want to do is look here at 23.8, and we'd expect to see it at one of these peaks. Because this is where the most vibration is happening, so we know that it's at a peak, or at least very close to one of these peaks. Then we have our low voltage differences here, and we're expecting to see those hit right at 0. So this one is at, I think is 23 or so. I don't remember exactly. So we come in here and it would be hitting right about here, or right around 0. And those are the positions that are staying the same and are not vibrating in this beam. And so now you see when I ran into a problem. And you notice the difference between this and that? There's no difference. So I didn't realize that until we started comparing data, and that means I need to do a little refining of the programs because they should not be exactly the same, since one is a 4th order and one is a 2nd order. But we do a similar thing here, and comparing what these two, how close this matches up with our model is what's going to determine which one is more accurate. And once I get this worked out, we have really good data to be able to do that and compare the two of them. I'm sorry, there we go. So, using the explicit finite difference method, I created these two models that really, they need a little more refinement, I've come to realize, but I was pretty happy with the data that we took. We've got some very obvious points where there are nodes and antinodes, and I would like to put a little more data, have a little more data to work off of, perhaps doing a couple more frequencies, but with a little refinement of the programs, I think it can be very well combined, compared between the two models. There we go. So a big part of right now is what I want to do further on this. There's so much more, so much deeper that you can get into both of these models as well as the actual interferometry. So I was looking at, and I think one of the issues I was having with the models is with the driving force. We used a small piezo patch which creates a tiny vibration in the beam through an electrical current on one end of the beam, which I don't think I got that into the model quite correctly, which would be part of the reason it's not turning out the way I was expecting. Also not accounting for any internal damping of the beam or the natural frequencies of the beam, which I think would definitely be, I think that is where I would like to start if I was going to keep going on this, is to look at the actual natural frequencies of the beam and match up my frequency that I'm measuring at with those frequencies. And then I'd also like to look at a few other things, looking at what different materials have an impact on this. We use pretty simple aluminum alloy, but what would a copper or something do, and how well can we model that change in the material in the actual models? Because I think that would be interesting to look at. At different thicknesses, I've seen a lot of studies about this stuff with some very, very, very thin beams. And I'm curious to see how well the wave equation would model the vibration of a thicker beam. Because every time I've seen the wave equation applied to a beam, it's been less than a millimeter or so beam. And then I'd also like to look at a different driving method. Clearly I didn't quite grasp this one in the model quite as well as I should have. And so I'd like to look at what impacts just having other methods of driving, whether it's placing a weight on the cantilever and letting it go, which is a pretty traditional way to start it in motion, and then we get free motion, or the piezo or some other type of driving method. And so I'm not entirely thrilled with where this ended up. I was really hoping to have more substantial conclusions about it, but I'm pretty happy with at least the data it took. And I know where to go from here with it for sure. There's a lot more in depth you can get, and I'm pretty happy with that part of it. Any questions?
Hey, really quick, I also wanted to thank the Applied Math Department, especially John David, because as much as I like to say I'm an expert in solving fourth order differential equations, not even close. So thanks, John. All right, anybody got any questions?
Yes.
Okay, so what was the amplitude of the piezo that you were driving this at?
I didn't actually calculate it. It was less than. I looked it up, and I don't have it off the top of my head. I can look it up again and let you know. But it was less than a millimeter amplitude, which is less than.
Yeah, I was imagining it was very, very small.
It's very small.
Have you thought about just doing it as an experiment, clamping both ends and driving the piezo? Then you could model it as a standing wave and kind of have an idea of where you would expect nodes and antinodes to be, and then running your experiment to see if you can detect those nodes and antinodes.
Yeah, and that was kind of the idea here, because even with it being cantilever, it still acts as if the free end is,
But in that case, you would have an
secure.
idea of where the nodes and antinodes should be,
Yes.
and you would have an idea of where your
Yeah, that'd probably be a good way to refine models for sure.
and what's the resolution on your interferometer that you're using? I mean, were you able to detect the change in the micron distance?
Yes, it was coming up with a pretty big voltage difference between the two of those. We can't detect the direction, but that wasn't necessarily
Just
something.
one more, did you move your setup every time, or did you move your beam?
Moved the beam every time. So the setup stayed where it was. Moved the beam slightly every time, which definitely brought some error into it, I think, because human error, there's some changes and differences, and not always was that beam perfectly lined up every time we did it. But if I had a chance, I'd like to build something to actually move the beam. But that would be some kind of engineering problem, and I'm not an engineer. Do you have your question?
Well, I suppose you could have put it on, one, I can't remember the name of it now, but one of the things you can just twist and moving it small amounts. I mean, it seems like you probably could have, I mean, you could have run it, I don't know, between Vargas's lab or Thompson and picked up one of those and then attached it to the table and then just turned it to move it ever so slight amounts. Like that
So we looked into that. I've got some stages down in my lab. The problem is they only move 2 inches or something like that. To get
Okay,
something
so
that moves 24 centimeters. And
So eventually you have to, yeah.
Yeah, so it's,
And so they don't, you know, generally
that would have been
have
ideal.
to make ones that are 24 centimeters
Yeah.
and move with, you know, sub-millimeter
Right.
precision.
so that's kind of what I was referring to. I'd like to create something that can do that, because I think that's a really good
You
idea.
got $10,000 or $15,000 you can spare.
Sure, why not?
Anything else?
How thick was the beam that you were vibrating?
Let me look. I have it. It was maybe I don't have it. I do not have it. It was
The order of a millimeter, less than
yeah. It was
1/16 of an inch.
point. I want to say 0.8 millimeters. Is I believe what it was. Yes, something close to that. I don't have it right here with me though. Yes.
Did you play with your boundary conditions at all for the fourth order to see if you could trigger a difference between the second order and the fourth order results?
Because I did a little bit, yes. The issue is that it came down to when I was troubleshooting, I was looking through that, but because the boundary conditions for everything was pretty much 0, the driving, the initial conditions made a lot more difference on how the wave functions turned out. The boundary conditions didn't have too much of an effect on it that I saw. And I think if I could get the driving function properly in there, that the boundary